In this video, I want to help you gain an intuitive understanding of calculus and of derivatives. Now, maybe you're thinking that you haven't seen calculus since your college days, and depending on when you graduated, maybe that was quite some time back. Now, if that's what you're thinking, don't worry. You don't need a deep understanding of calculus in order to apply neural networks and deep learning very effectively. So if you're watching this video or some of the later videos and you're wondering, wow, is this stuff really for me? This calculus looks really complicated. My advice to you is the following, which is that watch the videos, and then if you could do the homework and complete the programming homework successfully, then you can apply deep learning. In fact, what you see later is that in week 4, we'll define a couple of types of functions that will enable you to encapsulate everything that needs to be done with respect to calculus. There are these functions called forward functions and backward functions that you learn about that lets you put everything you need to know about calculus into these functions so that you don't need to worry about them anymore beyond that. But I thought that in this foray into deep learning, that this week we should open up the box and peer a little bit further into the details of calculus. But really all you need is an intuitive understanding of this in order to build and successfully apply these algorithms. Oh, and finally, if you are among that maybe smaller group of people that are experts in calculus, if you're very familiar with calculus or derivatives, it's probably okay for you to skip this video. But for everyone else, let's dive in and try to gain an intuitive understanding of derivatives. I've plotted here the function f of a equals 3/8, so it's just a straight line. To gain intuition about derivatives, let's look at a few points on this function. Let's say that a is equal to 2. In that case, f of a, which is equal to 3 times a, is equal to 6. So if a is equal to 2, then f of a will be equal to 6. Let's say we give the value of a, just a little bit of a nudge. I'm going to just bump up a little bit, so that is now 2.001, right? So I'm going to give a like a tiny little nudge to the right. So now is, let's say, 2.001. And this plot isn't to scale. 2.001, the 0.001 difference is too small to show in this plot. Just give a little nudge to the right. Now f of a is equal to 3 times that, so 6.003. So then plot this over here. This is not to scale. This is 6.003. So if you look at this little triangle here that I'm highlighting in green, what we see is that if I nudge a 0.001 to the right, then f of a goes up by 0.003. The amount that f of a went up is 3 times as big as the amount that I nudged a to the right. So we're going to say that the slope, or the derivative, of the function f of a at a equals 2, or when a is equals 2, that the slope is 3. And the term derivative basically means slope. It's just that derivative sounds like a scarier, more intimidating word, whereas slope is a friendlier way to describe the concept of derivative. So whenever you hear derivative, just think slope of the function. And more formally, the slope is defined as the height divided by the width of this little triangle that we have in green. So this is 0.003 over 0.001, and the fact that the slope is equal to 3, or the derivative is equal to 3, just represents the fact that when you nudge a to the right by 0.001 by a tiny amount, the amount that f of a goes up is 3 times as big as the amount that you nudged a in the horizontal direction. So that's all that the slope of a line is. Now let's look at this function at a different point. Let's say that a is now equal to 5. In that case, f of a, 3 times a, is equal to 15. So let's say I again give a nudge to the right. A tiny little nudge, so it's now bumped up to 5.001. f of a is 3 times that, so f of a is equal to 15.003. And so once again, when I bump a to the right, nudge a to the right by 0.001, f of a goes up 3 times as much. So the slope, again, at a equals 5 is also 3. So the way we write this, that the slope of the function f is equal to 3, we say d f of a dA, and this just means the slope of the function f of a, when you nudge the variable a tiny little amount, this is equal to 3. And an alternative way to write this derivative formula is as follows. You can also write this as d dA of f of a. So whether you put the f of a on top or whether you write it, down here, it doesn't matter. But all this equation means is that if I nudge a to the right a little bit, I expect f of a to go up by 3 times as much as I nudged the value of little a. Now, for this video, I explained derivatives, talking about what happens if we nudge the variable a by 0.001. If you want the formal mathematical definition of derivatives, derivatives are defined with an even smaller value of how much you nudge a to the right. So it's not 0.001, it's not 0.00001, it's not 0.00000, and so on 1. It's sort of even smaller than that. And the formal definition of derivative says whatever you nudge a to the right by an infinitesimal amount, basically an infinitely tiny amount. If you do that, does f of a go up 3 times as much as whatever was the tiny amount that you nudged a to the right. So that's actually the formal definition of a derivative. But for the purposes of our intuitive understanding, we're just going to talk about nudging a to the right by this small amount, 0.001. Even if it's 0.001 isn't exactly, tiny infinitesimal. Now, one property of the derivative is that no matter where you take the slope of this function, it is equal to 3. Whether a is equal to 2 or a is equal to 5, the slope of this function is equal to 3. Meaning that whatever is the value of a, if you increase it by 0.001, the value of f of a goes up by 3 times as much. So this function has the same slope everywhere. And one way to see that is that wherever you draw this little triangle, right, the height divided by the width always has a ratio of 3 to 1. So I hope this gives you a sense of what the slope, what the derivative of a function means for a straight line, where in this example, the slope of the function was 3 everywhere. In the next video, let's take a look at a slightly more complex example where the slope of the function can be different at different points on the function.